Thank you for the introduction, and I would like to thank the organizers for having me here. I'm really excited to be here. It's an excellent workshop, and it's a wonderful place to be at with roosters and geese outside, and it's fantastic. I will, and also Ron promised that I would share a lot of equations about the cis effect, but I will not, because this is the title. So I will not talk about the cis effect per se, but it will come up a little bit. There could be a few formulas, I'm afraid, but you're going to have to sort of deal with that. These are my collaborators, which I would like to sort of also acknowledge for this work and for a few others. And Furkan Öztürk specifically gave a reason for the title of this talk, in a sense. Well, we wrote a paper with that title. So actually, Furkan gave me sort of a very interesting point of view to magnetism and the cis effect and so on. This is chemistry. I don't know anything about it. But apparently, I mean, you have a chiral molecule here. You have magnetite. It's ferromagnetic, but it's not sort of magnetized, but it has domains. And there is an interaction, it seems, between the molecule and the magnetic material. And this interaction is good for this reaction here in this step when this molecule called Rao, well, it's something that I cannot sort of pronounce. It's this molecule, and it is chiral, always. It's a D enantiomer or L enantiomer. And the question is, so this is an interesting molecule also because it's a precursor of RNA, which is sort of essential for all life forms on our planet as we know it. And life is homochiral. So the question is, how does it become homochiral? That's what he's interested in. And that's why he's been looking at the interaction between chiral molecules and magnetite. And that's where we think the cis effect comes in. However, this is not what I will talk about, the cis effect per se, but I will talk about this that they found. So what is very interesting when you sort of, you have your magnetic substrate here is nickel in this picture, but it could be magnetite, but I think magnetite is just worse to work with. In principle, it doesn't matter. It's non-magnetized nickel with domains. So you have the bare substrate, and you look at the sort of the magnetization curve here. It looks kind of temperature independent. Well, and you have some coercive field here at some point, and so on. And you can see how this coercive field is more or less constant with temperature. And then you put on these Rao molecules, homochiral set of Rao molecules, on the nickel here. And first of all, you can see how the loop is actually widened.
Excuse me. Homochiral, it means that you have a racemic...
No, homochiral means that you have one sort.
Oh, one sort.
L or D, but not both. Okay, so you see how it widens. So first of all, then obviously, putting the Rao increases the coercivity. That is fascinating in itself. But that's not the most fascinating part. I think this is the most fascinating part, that the coercivity actually increases with temperature. And this is a phenomenon which kind of goes against most of magnetism theory that we know, because oftentimes with temperature, magnetism tends to sort of be destroyed. But this is not the unique example. There's been sort of, this been observed before, a few times at least. Well, 2 times. Is that a few? I don't know, but it's 2 at least. You can see here, this is sort of a bipartite lattice of paramagnetic and diamagnetic tallocyanine. And the paramagnetic version has iron, and the diamagnetic has a zinc fluoride sort of dressing. But this crystal, bipartite crystal, is kind of ferromagnetic with increasing coercivity with temperature. Also here, there are 2 examples. Yeah, there are 3, so there are a few. These are 2 different chiral crystals with copper centers here. These orange ones are copper. And so it's a 2 plus, right? 2 plus, yeah. So it's a magnetic element, but without the chirality, it's kind of paramagnetic, perhaps at best. But this is quite ferromagnetic with an increase in coercivity also. Both of these are. So it's not sort of one example. There are at least 4 now. Maybe there are more. I don't know. So I will talk about how can we sort of, what can we do with magnetism that tends to go against what we know from theory. And this is not why I made this picture. This is just because I wanted to make something look fantastic. I don't know. But in principle, you have your transitional metal spins here, localized spin moments. And then you have electrons. And the electrons, they mediate interactions between the spins. That's what is known as the RKKY, for instance, and so on. It's this indirect spin-spin interactions. And if these are also moving back and forth, sort of like we talk about here, then you can ask, will this motion also have an influence on the magnetism? And which influence will it have? I mean, obviously there will be an influence. The question is which. Will it only be destructive or could it be constructive? So I'm making a very simple assumption here. So I'm taking a Hamiltonian where I have a metal, say, or an oxide. I mean, it doesn't matter. We have an H0 with a very simple description of some electronic structure. But in this electronic structure, I have a sort of a spin-spin interaction. So it's a Coulombic part between, say, the itinerant electrons and the localized electrons, say, if you have S and P and D orbitals and so on. So this would be the D orbitals, and this would be S and P, and so. But it's a Coulomb interaction. And then we have the electron-phonon interaction, where I have this sort of the electron charge, and here I have my motion, and there is something in between. So starting from this, I can now derive an effective model for the interaction between the Q and the M. And this is what it looks like. Okay, it's an expression. But here we have the Q, the displacement sort of coordinate that interacts with itself. So phonon-phonon interaction. And I have also magnetism interacting with magnetism. So it's RKKY, if you wish. And then we have Q times M and M times Q. So we have a connection between the magnetic part and the lattice part through these tensorial interaction susceptibilities, you could say. It doesn't couple directly to Q. It couples through this tensor. Yeah, but this tensor, it comes from, it contains the electronic structure of your host material. So that's essentially the H0. This H0 here. That's what sort of is in this tensor here. So it is. I assure you. Look, anyway, this is kind of like a magnetic field acting on a spin. You can view it like that. There's no problem with symmetry, I assure you. Anyway, so I'm interested in to see, okay, this is a mathematical exercise. This could be 0 for all we know. I don't know, but so that's the job, right? To figure out what are those tensors. Could there be something? And it turns out that they are non-vanishing if H0, if the electronic structure in my background has either some finite spin density, that is if it's already itinerant ferromagnetism or antiferromagnetism or something like that, right? Or some other type of structure. Or if there is a spin-orbit coupling. So spin-orbit coupling will actually help me to give a connection between the spin and the lattice. So in principle, I don't need number 1 here. I could leave with number 2. And spin-orbit coupling we know is always around. Smaller or larger, but it's always there, right? So in principle, this coupling will always be there, but then it's a matter of how large it is compared to everything else. But okay, so I can at least assure myself that it's going to be there, and there's no question about it. With this, we can also extend the sort of, so go into the classical limit here, you could say. we can extend the sort of equations for magnetism dynamics and lattice dynamics. So here is essentially the Landau-Lifshitz-Gilbert equation in a quite generalized form. Without the Q part here, you would sort of retain the LLG equation, but here we have this additional component that also couples directly to the lattice, which is natural, of course. If you have it in the Hamiltonian, there should be a coupling between the subsystems. And the same thing here with a driven harmonic oscillator, well, it's not harmonic anymore, but with a driven oscillator, you have sort of all the mechanical parts here, and then there is a connection to also the spin part here in that. So you will you should be able in principle to drive your oscillations with a magnetic thing here. I haven't explored this. This is just sort of more fun. What can you derive and what can you not? Anyway, but this type of discussion actually helped us understanding. This is the cis effect thing. This helped us understanding the increase of the efficiency of the cis effect with temperature. So this is backwards. This is I would never plot like this. So here we have 300 Kelvin, and here we have 150 Kelvin. So it's kind of backwards, but it goes up. So it's a poor cis effect for low temperatures. It's a strong cis effect for high temperatures. Again, it seems to go against intuition when it comes to magnetism. But actually, and this molecule, it's huge here. It's a kind of protein, but it also has these transition metal centers. It's copper again. It's a 2+. So the idea we have here is that the copper center, well, it sits in a chiral environment, and then it vibrates. Well, something in this environment vibrates, at least, the chiral molecule or whatever. And the vibrations stabilize the spin moment. So at low temperatures, the potential where the spin sits in, or the nucleus sits in, is nearly harmonic, which means that there's no displacement of this copper in net, right? So there's no net moment, no net force acting on the spin. But when you increase temperature, you start to excite modes which are anharmonic in the potential. And these actually exert the force on the spin, which has the form of a magnetic field. And so with this idea, sort of, we could calculate the effective magnetic field exerted by the vibrations on the spin, and it has this increase. This is a logarithmic scale here, 10 to the minus 6 up to 10 to the minus 3 EV, and you go from 0 to 350, 400 Kelvin or so, and it increases. And the cis effect increases also. But so to summarize that picture, essentially, for low temperatures, we have a sort of isotropic environment for the spin, which makes this sort of super paramagnetic. It doesn't have a direction. But with the increase in temperature, there's an anisotropy acting on the spin, which wants to point in a certain direction. And therefore, the cis effect also increases. And we can formulate it effectively like sort of S has sort of B fields exposed on it, and an additional B field that actually has to do with the displacement of the nucleus. That's a way to explain it.
So I don't understand. So gamma is the number? Yeah.
What's that?
So in your equation, gamma is the number?
Gamma?
Yeah. No, the second equation, second term. Yeah.
T, tau.
Okay.
Yeah.
So it's a number, right?
No, yeah. It is. I mean, so effectively, this is a vector times S.
It's a time level.
No. There is no issue. So because this is not a constant, dimensionless constant. This has dimensions.
Yes.
And it's a vector.
Yes.
Yes, and the dimensions make this to a magnetic field. We can go through it afterwards, but I mean, if you don't have a problem with this, I don't see why you have a problem with this.
Because it's not
Because you have a Q here. But what if the dimensions of this is 1 over q times the dimensions of the B field. I mean, there's no problem.
Unless gamma depends on S.
It's not.
Or T depends on S.
I'm telling you, there is a spin-orbit coupling here.
Yeah.
And that what sort of picks up the thing. But it is time reversal odd, this tau. As it should be. Anyway, so now having this action, now that I established that it's there and it works somehow, I want to see what could it do if I just sort of think freely around it. What would these tau SC and, well, these Q times M and M times Q, what would those terms do to the physics if I just allow them to be whatever? And that's what I'm doing next now. So I'm taking a spin dimer, so 2 spin half atoms, you could say, and then I look at it's a 4-dimensional Hilbert space. So I look at this many-body sort of spectrum in a Heisenberg model sense. Well, you can actually see the model here. So I have 2 spins interacting isotropically, and then there is a singlet, then there's a triplet, and so on. If you only have J, and if I now add on first this Ising term, which is kind of anisotropic, symmetric, you can split up the triplet state a little bit into a doublet here and a singlet here, and the singlet is untouched. And finally, this term, A times Q, which comes from my sort of derivation, this one also acts on S. So it actually splits up this doublet in a weird way. And if A is strong enough here, you can actually go from having a singlet ground state to have this S plus or minus 1 state as ground state. So you can actually change the physics, pretty much. Well, this is kind of what I could do should I have the model. But of course, you can ask, so where do you have a dimer? Well, actually, I do have dimers just a little bit of everywhere. So take a model for say, this chiral structure here. I have, so I'm taking the effective model for the spins. So I have some Hamiltonian for each individual spin here. I have a Hamiltonian for the vibrations in the system. And I say that there is a coupling between the vibrations and the spin like this, like I have derived, and there is a spin-spin coupling. I'm just saying, okay, so this is now an extended crystal. So I can go to reciprocal space, which I do now. And then with some assumptions, of course, there have to be assumptions always, but I retain the dimer, right? In K space, it's not a real space dimer, but still a dimer, right? So I have a dimer between K and minus K, and K and minus K. So I can apply the same sort of thoughts that I had here to this dimer, but I do it in K space instead. And doing that calculation, I do sort of calculations here for spin 1/2 system for a crystal now, so where I integrate over K space and so on, and then I change my A, I call it alpha here. It's really a little unfortunate, but the alpha is essentially this part, right? So I change my alpha from negative to positive. I change my exchange interaction from negative to positive. And this is the phase diagram that I sort of map out. And it seems to be sort of very much ordered in a ferromagnetic sense. And it has a little antiferromagnetic order there. And I can actually go from antiferromagnetic to ferromagnetic should the interaction between the lattice and spin be strong enough. And I can do the same thing with spin 1 and 3/2. And this is actually an exact calculation. This is the formula that you can do. And then you have the sum over K space, of course. But nonetheless, I mean, it's more or less exact. Again, it's just alpha is just a parameter. So I need to now, can I justify this alpha in some way? And yes, with harmonic vibrations, I cannot justify alpha, or I can say that alpha must be 0. But if I do have anharmonic vibrations in my system, and you all talked about that, and we saw a lovely talk this morning about anharmonicity, so I'm becoming confident that there are. if you have sort of anharmonic terms, you will actually have something. This alpha has an interesting behavior for a temperature behavior. So this cos hup, it's proportional to the alpha that I'm talking about. So it increases with temperature should the frequency of the vibrations be fairly low, 1 millieV. And it's nearly constant if the frequency is very high. So slow vibration seems to be good to enhance this coupling between spin and lattice. So okay, let's take a small vibration and see the temperature dependence now. So now I'm coming more to a calculation. Alpha is not just sort of something made up, but it comes from the model now, calculated. And here we can look at the phase diagram. If I sweep my exchange interaction and I sweep the temperature with different frequencies here, and the color scale is that high spin for yellow colors and low spin for blue colors. So high vibrations, well, it doesn't seem to give much of order, but okay. But it gives something for low vibrations. Anyway, so I'm nearly out of time, but I'm going to try to finish up where I started. Come back to this raw molecules now, and why do we see the increase of this corrosivity with temperature? So I can actually work more or less with the same model that I had from the beginning. It's written in a different form here, but it's again just the localized magnetic moment here, and I have the lattice variation. And then I do a linear spin wave approximation because I want to look at the magnon spectrum, because the magnon spectrum tells me something about whether it's ferromagnetic or not. So the magnon linear spin wave approximation, it gives me a magnon density here, so that's a sort of a bilinear term, and here I have a connection between creation and destruction of magnons coupled to this motion. And so what we're saying with this model is essentially, or what I'm calculating with the model is essentially, if I don't have Q here, if I don't have the lattice motion, then my magnon spectrum for a ferromagnet, it's sort of quadratic. And I come in with temperature here. There's 300 Kelvin or so. So I come in with temperature, so I can excite the modes that sit in the magnon spectrum. So I can start to destroy my magnetization. That is what magnons do, right? They destroy magnetization. But suppose I was able to divert this excitation and not exciting the magnon, but instead exciting the phonons, then I would maintain an empty magnon spectrum, that is, no magnons. I would maintain my magnetization. So if I can lose this energy back to the or into the phonon system, I will actually maintain my magnetic moment strongly. And so effectively it means in a way that you require higher energy in order to excite your magnons than you would without the phonons. So in principle, you could say the gap here, the spin gap, has been increased. And this is calculated through sort of diagrams. It's just a second order theory. It's not very complicated. But I would want to sort of stress this diagram is kind of redundant. It doesn't do much. This complicates things, but it doesn't do much interesting either, actually. This is the one that actually does something. So this introduces a shift into the magnon spectrum. It actually, you can compare it with an anisotropy. So when this diagram is doing something strongly, this gap will increase. So this diagram is what takes you from here to an effective increased gap. And with that, yeah, I can calculate now my new effective sort of dispersion relation given the old, and there's a sort of a logarithmic kind of correction, which is temperature dependent with the beta here. And because of this form, you're going to have sort of an increase of your dispersion or this anisotropy with temperature, essentially. So this is a calculation of the sort of anisotropy increase as function of temperature. So, and with that, it was great. Thank you very much for your attention.